Hello. Today I'll describe integrator drift and its effect on satellite orbit simulator error. Then, I'll show you how to test the satellite orbit simulator software for these errors. In the image I show on my right, you see a mathematical flowchart for the spacecraft's equation of motion. To simulate a near-Earth satellite orbit, this equation must be solved iteratively while incrementing time. As you can see in the image, the total acceleration felt by the spacecraft is the summation of those gravities due to the Sun, Moon, and Earth, plus acceleration perturbations due to Earth bulge, Earth atmosphere, thrust, and solar radiation. Note that two integrators are required to convert spacecraft acceleration to spacecraft position, r. First, we integrate total acceleration as a function of time to get velocity, and then integrate the velocity as a function of time to find position. Then, this new position is used to find the updated acceleration due to Earth gravity. Of course, Earth bulge, atmospheric drag, and solar and lunar gravities are also a function of spacecraft position, but showing these in the image would unnecessarily complicate the flowchart. Integration is simply a repeated summation. To produce zero spacecraft position errors at the output, the time step would need to be infinitely small, resulting in an infinite number of integrations. Since this is not practical with digital computers, we use a time step that is small enough to reduce errors to an acceptable level, but large enough to keep the calculation time short. In this software, our default time step is 1 second. Therefore, a 100-day simulation will require over 17 million integrations. Modern personal computers can do this in less than 10 seconds. This software now has 3 numerical integrators that you can choose from. These are the semi-implicit Euler, velocity Verde, and Runge-Kutta fourth order. Unfortunately, since the integrator output is used to calculate the integrator input for the next loop, integrator errors accumulate over time. Based on the mathematics involved, we believe that the Euler method will be fast but less accurate, while the RK4 method will be slow but more accurate. The Verde method should be a compromise of the other two for both speed and accuracy. Here we show you the results of our accuracy tests. To measure integration errors, our test simulation must run as long as possible to see the error due to integrator drift. The simulation duration limit for SOS is 1 second less than 100 days. To isolate the integrator error from other sources of error, we removed all accelerations except for Earth gravity, resulting in the mathematical flowchart I show on my left. Note that acceleration is represented by r with 2 dots over it, and velocity is represented by r with a single dot over it. This represents a perfectly spherical Earth with no atmosphere. Also, there is no thrust and no gravitational forces due to the Moon or Sun. Finally, there is no force due to solar radiation. Note that I have opened the ISS Orbit example project file, where Euler integration with 1 second integration step time is the default setting. Previously, I set the simulation time span to 99 days, 23 hours, 59 minutes, and 59 seconds. Then, I removed acceleration sources by unchecking these boxes. 1. Earth bulge and atmosphere in the Earth group box. 2. Moon gravity in the Moon group box. 3. Sun gravity in the Sun group box. 4. Solar radiation in the satellite group box. Finally, I unchecked the satellite orbit steps box in the display group box. Now, I recalculate the simulation. If there are significant integrator errors in the simulation, you will see drift in the orbit position as time progresses. Zoom in to look closer. The orbit drift is so small that you cannot see it. In fact, the semi-major axis has drifted by only 12 meters. However, this may not be the best way to measure orbit drift error. We also measured the spacecraft's position error after 100 days, and that value was 4,586 kilometers. But, to measure spacecraft position error, we must know where the spacecraft should be after 100 days. Since the RK4 integrator is more accurate, we chose it, set the integration step time to 0.1 seconds, and recalculated the orbit. We then assumed that the final spacecraft position was the true position, and used it as our reference for accuracy. We ran this test for all three numerical integrators, and measured the speed and accuracy based on the final spacecraft position after 100 days. These results are shown on my left. I recommend that you pause this video and study this chart in detail. The information here will help you choose the numerical integration method that suits your needs. We hope you found this video informative. If so, please give it a like. If you want to be notified when we add more videos, click on the notification bell. Finally, leave a note if you have comments or requests for new videos. Goodbye.